All right, welcome to our latest explainer. Today, we are diving into some seriously game-changing technology in the fight against climate change. It's a potential breakthrough called electrochemical carbon dioxide capture. And it might just completely redefine how we clean our air.
Think about that for a second. We're not just talking about cutting back on emissions anymore. The real goal here is to actively remove the CO2 that's already floating around up there, and to do it with some really innovative chemistry that's all powered by clean electricity. So let's break down how it all works. This is the reality check. Right now, the concentration of carbon dioxide in our atmosphere has climbed to an unprecedented 422 parts per million. And it's this number that's lighting a fire under scientists and engineers everywhere, driving this urgent hunt for solutions.
So the big strategy to tackle this problem is known as CCUS. You can think of it as a whole toolkit for grabbing CO2 from big industrial sources, or even, and this is the really exciting part, pulling it straight out of the ambient air. This is just a critical piece of the puzzle if we're serious about getting to net zero.
What we're looking at here is a fundamental shift in how we think about this problem. For decades, carbon capture has been all about heat. You have to burn a ton of fuel to generate massive amounts of heat just to make the process go. It works, sure, but it's incredibly energy intensive. This new approach, it's totally different. It's driven by electricity, and that simple change opens up a whole new world of possibilities. Higher efficiency, smaller modular systems, and a direct plug-in to renewable energy.
To really get why this new electrical approach is so important, we first need to take a hard look at the limitations of what we've been doing so far, the current industry standard. Okay, so the current gold standard, a process called amine scrubbing, it comes with some serious baggage. It slaps this huge energy penalty on power plants, forcing them to burn up to 30% more fuel, just to run the capture system itself. And get this, more than 60% of that energy is just for one step: reheating the chemicals, which are often volatile solvents like MEA. On top of that, the upfront capital costs are just staggering. We're talking hundreds of millions of dollars for a single project. It's pretty clear we need a smarter way forward. And this brings us to that new approach, which sits right at this fascinating intersection that we love to explore here, the E3 nexus, where energy, the environment, and the science of electrochemical interfaces all come together. This is ECC, electrochemical CO2 capture. And what's so cool is that the idea itself isn't brand new. The basic concept was actually figured out way back in the 1960s to scrub CO2 from the air inside spacecraft for astronauts. Now that same idea is being totally reinvented for a much, much bigger mission. Using electricity to make a material grab onto CO2 and, this is the key, let it go whenever we want. So how does it work? Well, one of the most common methods is called a pH swing, and the best way to think about it is like an electric sponge. First, you apply an electric current. This makes a solution alkaline, or basic, which causes it to just soak up CO2 from the air. Then you just reverse the current. This makes the solution acidic, which basically squeezes the sponge and releases all that captured CO2 in a pure stream. Now, of course, it's not a literal sponge. The real magic is all happening at the molecular level. It's powered by these special molecules called mediators. They're the real workhorses here, doing the actual job of grabbing and letting go of the CO2 just by responding to that electrical signal. And there are two main ways they do this. The first strategy uses what you can think of as molecular taxis. In this case, a mediator molecule gets an electrical charge, which makes it bind directly to a CO2 molecule. Then, when you flip the charge, it just lets it go. The second strategy uses proton pumps. Now, these molecules, they don't even touch the CO2. Instead, they use electricity to shuttle protons around, which is what causes that pH swing we just talked about, creating the perfect conditions for capture and release. Now, this all sounds pretty fantastic, right? But ECC is still an emerging technology. It's really on a scientific quest. And like any great quest, there are definitely some big hurdles to overcome before this thing is ready for prime time. To make it, this tech has to hit some really key performance targets. How much electricity does it actually take per ton of CO2? How fast can the system run? How much of that precious electricity is actually doing the work versus just being wasted as heat? And, maybe most importantly, can the materials last for thousands of hours of operation? And can we actually scale this up from a tiny lab setup to something that can handle the output of a power plant? These are the big questions. So let's look at a quick report card. This snapshot of different ECC methods really shows you the trade-offs involved. Some approaches, they're pretty energy efficient, but they're just way too slow to be practical. Others are super fast, but man, they use way too much energy. But then, there's this one process, electrowinning. It seems to be hitting a potential sweet spot, really low energy use and high speed. This is where a lot of the excitement in the field is focused right now.
And here it is. This is the number to beat. This is the energy cost of that old-school, traditional amine scrubbing process we talked about. It's the equivalent of about 1.3 gigajoules of work for every ton of CO2 captured. This is the benchmark that all new technologies are chasing.
And putting that all into perspective really tells the story. Look at this. The traditional method clocks in right there at 1.3 gigajoules. Some of the new ECC methods are still using more energy than that. But then look at electrowinning. It's already showing energy use below that commercial standard. This is a huge deal. It's proof that the real-world potential of this research is absolutely there.
So, seeing that kind of incredible progress naturally makes you ask, okay, what's next? Where is all this research heading? And what are the breakthroughs on the horizon that could finally push this technology into the mainstream?
Well, it's a journey, right? It's a path from the lab bench to the real world. Right now, most of these ECC systems are lab prototypes. The next absolutely critical step is pilot-scale testing to prove they can work outside the perfect controlled conditions of a lab. From there, it's on to full demonstration and eventually commercial projects. And getting to that next stage is going to take breakthroughs on a whole bunch of different fronts. We're talking about engineering smarter molecules that have the perfect grip on CO2, not too tight, not too loose. We're talking about building better reactors with advanced materials, using AI and simulations to optimize every little detail, and being smart enough to borrow proven ideas from other mature industries, like water desalination. But maybe the most powerful part of this whole vision is the incredible synergy with renewables. Because ECC runs on electricity, you can power it directly with solar and wind. Just imagine that for a second. Using clean energy to run a system that cleans the air. That is the key. That's how you create a truly sustainable circular carbon economy. So, after seeing all the science, the challenges, and the incredible potential, what does this all mean for the future? And maybe more importantly, for anyone watching who's inspired by these ideas. Look, there are never any guarantees in science, but the progress we're seeing is just incredibly promising. The fact that researchers are already getting the energy use below the current commercial benchmarks is a major, major milestone. This technology really could become an essential tool that helps us move beyond just slowing down emissions to actively reversing the buildup of CO2 in our atmosphere. This whole journey, from a lab idea to a global solution, it's driven by curiosity, by persistence, and by innovation. So for all the students, the engineers, the scientists watching this right now, the next breakthrough could absolutely come from you. The challenges that we've talked about today, those are the opportunities of tomorrow. And that's all for this explainer. From all of us here at the E3 Nexus, where we explore that amazing intersection of energy, environment, and electrochemical interfaces, thanks for diving in with us. We'll see you next time.